Hola, bienvenidos a todos a otra sesión del coloquio del Instituto de Matemáticas. Hoy tenemos el gran placer de tener con nosotros a Scott Aaronson de la Universidad de Texas en Austin. Scott es muy reconocido computólogo, especialista en computación cuántica, y nos va a hablar sobre la complejidad computacional y explicaciones en física. Thanks, Scott, for being here, for accepting the invitation, and go ahead.
Okay, all right. So, muchas gracias. Thank you so much. It's great to be back for my second visit to UNAM, actually. I had a wonderful time here 8 years ago, having a wonderful time now. Thanks for inviting me. And I wish I could have given this talk in Spanish, but we'll have to make do. So I'm going to talk about computational complexity and explanations in physics, which sort of ties together a bunch of different things that I've been thinking about over the whole course of my career, but also quite recently. Okay? So what is computational complexity? Okay, so I would define it as just the study of the inherent resources like time and memory, okay, but also other things like randomness or quantum mechanical resources that are needed to solve computational problems, and especially how those resources scale with the size of the problem that we're solving, right? Do they scale like the size of the input, or like the size of the input squared, or do they scale exponentially with the size of the input? And there are many different reasons why problems can be too hard to solve. And computational complexity or intractability is only one of those reasons. Right? A problem can be too hard to solve just because you are not given enough information about it, or you don't have access to all the data. Hey, this is the garbage in, garbage out problem, right? Problems of simulating physical systems sometimes can be hard because you cannot even get all of the relevant data consistent with the laws of physics. So for predicting the weather, for example, beyond a few weeks into the future, it probably doesn't even matter how powerful of a computer you have, right? Because of the butterfly effect, right? Because the tiniest inaccuracy in knowing the state of the atmosphere will get exponentially amplified over time and will eventually completely ruin your prediction. Okay, and then of course there's irrationality, there's cognitive biases, all of those things. Okay, computational intractability is specifically, when you have all of the data that you need to solve a problem, at least mathematically, you understand what the problem is, you are rational, but it's merely that it would require too much computation, too many steps or too much memory or something to get the answer. Alan Turing, founder of computer science, insofar as there is one, died before computational complexity was really a field, but he did co-found the very closely related subject of computability theory, right, where we study what is computable in any amount of time. And what is not computable, even with unlimited time, like the halting problem or the busy beaver function, things like that. Okay, but for almost anything in computer science, you can find some quote from Alan Turing where he anticipated it, and complexity is yet another such example. Right, he has this wonderful quote: "The view that machines cannot give rise to surprises is due, I believe, to a fallacy to which philosophers and mathematicians are particularly subject. This is the assumption that as soon as a fact is presented to a mind, all consequences of that fact spring into the mind simultaneously with it. It's a very useful assumption under many circumstances, but one too easily forgets that it's false." Okay, so that will directly be relevant to us here. We're interested in sort of what happens to philosophy when we take into account that there are computational limitations. And specifically, we'll be interested in sort of what happens to our understanding of physics when we take that into account. So, it is clear, should be uncontroversial, that limits on computation can be relevant to our ability to know about the laws of physics. Okay, so what I'm showing here is some of the computing clusters that are used to analyze all the data that's been pouring out of the Large Hadron Collider in Switzerland since 2012 or so. Okay, and you just need a massive amount of computing power to analyze these sort of billions of particle events that are happening every second, and actually, a lot of potentially interesting data just gets thrown out, for lack of enough computer power to analyze it all. Okay, or enough, memory to store all of the events. Okay, so clearly, if we had more computing power, certainly if we had more of this kind of computing power, more brain power, we might be able to discover more about the laws of physics. Okay, but in this talk, I want to ask a question that is, maybe a little bit more philosophical, but hopefully for those here who come from computer science or from math or from physics, or from philosophy, there should be something in this talk for everyone, hopefully for other fields as well. Okay, but I want to ask: can computational complexity play a direct role in our explanations of the laws of physics themselves? Okay, and some people would say that it's really too anthropocentric for that. That is, like, it's too human, right? If we're saying that, a calculation is too hard for us to do, that doesn't say anything about nature, right? Maybe it's trivial for nature to do, right? And it seems like, computers are just machines that humans happen to build. If something is hard for our computers, that's just a statement about us, about our technology. That's not really a statement about the laws of nature themselves. Okay, so what I want to do in this talk is challenge that view. Okay, and I'm going to challenge it not through just sort of abstract argument, which I think would maybe be too boring for all of us, but I want to do it through a few case studies. Okay, where I think people have plausibly argued that computational complexity limits are really relevant to how we understand the laws of physics themselves. Okay, and these case studies, the first one will be about quantum computing, which is the main thing that I've worked on for the past 27 years or so. Okay, and but I'm going to talk mostly not about the practical problem of building a quantum computer, or about the practical things that a quantum computer would be useful for. Instead, I'm going to talk about sort of the original motivation that people had to think about quantum computing in the first place, which was really to understand quantum mechanics itself at a deeper level. Okay, and we're going to ask, what does the possibility of quantum computers, and in particular, sort of exponential speedups for certain computational problems, what does that mean for our understanding of physics? Does that provide a new type of argument for the many worlds interpretation of quantum mechanics, for example? David Deutsch, the co-founder of quantum computing, certainly thinks that it does. So we're going to examine that argument. Okay, and then the second thing I want to talk about is what I call the complexity theoretic Occam's razor, or sometimes I also call it Occam's razor, but with a computational aftershave. Okay, so we'll be asking, when we're judging physical theories, candidate theories, we know that the simplest theory is to be preferred, all else being equal. That's Occam's razor. right? But what do we mean by simplicity? You know, fewer entities postulated, fewer assumptions. In modern times, sometimes people would say simple means that there is a short computer program that can calculate the predictions of the theory. So that would be small in the sense of, you know, or simple in the sense of Kolmogorov complexity. Okay, but should we also be judging theories by how hard it is to calculate their predictions, right? If theories say that nature would have to solve an NP-complete problem or some other problem that we really think is intractable, then should a theory be disfavored on that ground alone? Okay, so that's a second thing we'll talk about. And then a third thing we'll talk about, and this is sort of a quite recent direction. Well, it grew out of work by Daniel Harlow and Patrick Hayden about 12 or 13 years ago, who were studying the black hole information paradox. Okay, the problem of what happens to information that falls into a black hole. This puzzle that Stephen Hawking raised back in the 1970s. And around 2013, Harlow and Hayden had a remarkable new proposal about black holes, which is that computational complexity seems like part of the explanation of what's going on. Okay, that there are certain experiments that seem like if you could do them in the region near a black hole, then they would cause a breakdown of the known laws of physics, specifically of general relativity and quantum field theory. But Harlow and Hayden argued that it's okay because to do this experiment would require an exponential amount of computation. Okay, and by the time that your quantum computer had, you know, done the relevant computation, the black hole would have already evaporated anyway. Okay, so maybe nature is sort of protecting our effective theories in physics, like, you know, general relativity, quantum field theory, not only by energy scales, but also by computational scales. Okay, so this was a quite new proposal. I'm going to talk about some recent work that I and others have done that also connects that idea to the second law of thermodynamics. Okay, and asking if we had enough computational power, could we engineer apparent violations of the second law? Could we make entropy appear to decrease? And so, you know, does the second law of thermodynamics also appear to be true only because of our computational limitations? Great. So let's dive into it. Okay. So part one is quantum computing and the many worlds interpretation. To explain how quantum computers can get such huge speed-ups, are we forced to posit the reality of parallel universes? So the first thing I should say, you know, this is people are here from all different backgrounds. What is quantum mechanics? You know, I'm not going to have time in this lecture to give a whole quantum mechanics course. Okay, but the good news is that quantum mechanics is actually much, much simpler than people say it is once you take the physics out of it. Okay, so the way that we like to think about quantum mechanics in, you know, my field, you know, quantum computing and quantum information is basically as a certain generalization of the rules of probability themselves. Okay, so in probability theory, you know, we might say that if I have a particle, I shoot it at a screen with a little hole in it, maybe the particle does something probabilistic. You know, that's already, you know, Einstein didn't like that. He didn't like that God might play dice with nature. We're not going to worry about that. Okay, if it was just probability, that would be fine, right? We could say that this particle has a probability P1, let's say, of hitting this spot if we shoot it at this screen with this hole in it. Okay, and then if a different hole was opened, like this one down here, then maybe this particle has some other probability, P2, of reaching that same spot. Okay, by the way, this is a photon. Okay, for my purposes, that's what it looks like. Okay, or it could be an electron. The logic would be the same. Okay, now what happens if both of the holes are open? Okay, that's the part that I care about. Okay, and then what we would say is that, not needing to know anything about the details of physics, right, just purely from the laws of probability, it is obvious that now the probability that the particle is going to reach this spot is simply P1 plus P2, right? Because, we just have to sum up the two different ways. Okay, this is the thing that quantum mechanics falsifies. This is the thing that when you do the experiment, you find that this is not the case. Okay, when you do the experiment, you find that actually when both holes are open, then often the particle will have a lower probability of reaching that spot than it would have had when only one of the holes was open. Okay? As if the two paths that the particle could have taken are interfering with each other. Okay? So the modern way that we explain that, modern meaning since 1926, so for exactly a century at this point, is to say that to each possible path that a particle could take, we need to assign a complex number called an amplitude. Okay? And amplitudes are very related to probabilities, but they're not probabilities. I mean, for one thing, they can be negative. They can be complex. Okay? And so let's say that I have an amplitude alpha 1 for the particle to go this way. I have an amplitude alpha 2 for it to go this way. Then the total amplitude for it to arrive at that spot, alpha, is just the sum of the two amplitudes for the two ways that it could have gone. Okay, so that's just like in normal probability theory. But now, to find the probability of seeing the particle here, when we look, we have to take the square of the absolute value of the amplitude. Okay? And now the result of this is that if, for example, one of the amplitudes was a half, and the other amplitude was negative a half, then when I add them up, I'm going to get 0. Okay? Which means P is 0, which means the particle never appears there at all. Okay? Whereas when only one of the holes was open, then I'm just squaring a half or negative a half, and then I get a quarter, and then the particle can appear there. Okay? This kind of thing, it's called interference, and it is the signature of quantum behavior, right? It's the sign that we're not just dealing with some little detail of particle behavior, we're dealing with a new foundation of probability itself. Okay? Yeah. So in quantum computing, what we're trying to do is to exploit this effect of interference, but at a massive scale. Okay? So a quantum computer is a device that would be made not out of bits, which have to be either 0 or 1, but out of qubits. Okay, so what is a qubit? A qubit is just a bit that has an amplitude to be 0 and another amplitude to be 1. So as we say, it can be in a superposition of the 0 state and the 1 state. Okay, and that's already interesting with one qubit. Okay, but when we have many qubits, then it's even more interesting. Okay, because if I have 2 qubits, then the rules are very clear that now I need 4 amplitudes. I need amplitudes for 0, 0, for 0, 1, for 1, 0, and for 1, 1. Okay, if I had 3 qubits, then I need 8 amplitudes. Okay, and if I have 1,000 qubits, which is not actually very many, that could mean, for example, the spin configuration of just 1,000 subatomic particles. Right? Then now I need, in general, 2 to the 1,000 power amplitudes. Okay? 2 to the 1,000 power is more atoms than there are in the whole visible universe. Okay? And yet, quantum mechanics has told us for a century that nature somehow keeps track of all of those parameters. Right? So it's as if just to keep track of what these 1,000 particles are doing, nature has to maintain some scratch paper that we never see, that's too large to fit in the whole visible universe. And whenever anything happens to those particles, nature has to cross off all the numbers on the scratch paper, all those 2 to the 1,000 numbers, and replace them with new numbers. Okay? That's a staggering amount of work for nature to go to, just to keep track of a few measly particles. And so it very quickly led to a thought, like if nature is going to all that work, if it's going to be so hard therefore for us to simulate on our existing computers, then couldn't we turn that lemon into lemonade? Okay, couldn't we build computers that themselves would take advantage of that same phenomenon of interference and of this exponential number of amplitudes? Okay, that was a really remarkable idea that Richard Feynman and David Deutsch and a few other physicists had in the early 1980s, and that's what gave rise to the modern idea of a quantum computer. Okay, but then people started talking about it, especially in the 1990s, and they were trying to explain this. The people started writing popular magazine articles about it, and they realized that they really didn't want to explain all this stuff about amplitudes and interference. That was too complicated. Okay, so they sort of hit on a way of explaining it that was much simpler and that sounded better. Okay, which is that they said, well, a quantum computer is just a computer that can try every possible answer in parallel, right? So, a classical computer has to try each answer one by one by one, but a quantum computer just tries each answer in a different parallel universe. And so then it can just instantly find the solution to anything, right? And that, people understood that, it explained why there's so much excitement about it. The only problem is that that's not really how it works. So let me try to explain what is wrong with that, okay? It's true that a quantum computer, can create this superposition over all the answers to your problem, even if there are exponentially many of them, okay? The trouble is that for a computer to be useful, at some point you have to look, you have to measure, you have to get an output. And if you just measured your quantum computer not having done anything else, then and it just had an equal superposition over all the answers, then the rules tell you that all you're going to see will be a random answer. Okay? Well, if you just wanted a random answer, you should have just flipped a coin in your pocket, 1,000 times. You could have saved all the billions of pesos to build a quantum computer, right? So the only hope of getting any advantage from a quantum computer is to somehow take advantage of the way that the amplitudes, being complex numbers, work differently from probabilities. So with every algorithm for a quantum computer, the game we're playing is we're trying to choreograph a pattern of interference such that for each wrong answer, some contributions to its amplitude are positive and others are negative. So on the whole, they cancel each other out. Whereas for the right answer, the answer we want all the different contributions to its amplitude to be pointing the same way. Okay? If we can arrange that, then when we look, we'll see the right answer with a high probability. Okay? If we don't see it, we can always run the computation again until we do. Okay? But crucially, there is quantum mechanics posits this sort of absolutely vast list of amplitudes, and yet we never see that list. How do we know that it was ever there? Well, only because we need it to calculate the probabilities of the various outcomes that we do see. Okay, so we need to exploit interference, and now the question is, what is that good for, right? And when Feynman and Deutsch and the others started thinking about quantum computing in the 80s, they could really only give one example of what a quantum computer would be good for. Namely, it would be good for simulating quantum mechanics itself. Okay? Now that seems kind of obvious, is kind of obvious, okay? And yet I would say 45 years later, that remains the economically most important application of quantum computers that we know, in my opinion, okay? It could be useful for discovering new drugs, pharmaceuticals, discovering, new ways to make batteries or solar cells, or ways of making fertilizer, right? These are all chemistry and material science problems involving many interacting electrons, where you have a very complicated wave function, a huge number of amplitudes, and where classical computers often struggle to give you an accurate answer in a small amount of time. People use supercomputers, and they use all kinds of heuristics and approximation methods to do the best that they can. But a quantum computer would give us a general purpose, programmable way of simulating nature at the quantum scale. And this is sort of what it's born to do. Okay? But this was not the discovery that put quantum computing on the map for most of the world. As I said, I think it's still the economically most valuable one that we know. But the application that really made the world pay attention to quantum computing was a different one. It came in 1994 when this guy, Peter Shor, discovered that if you could build like a large programmable quantum computer and it was error corrected, so like you could actually keep the qubits in their superposition state without it leaking out into the environment and so forth, then there is a fast method, a very, very clever, non-obvious method, where you could choreograph this interference pattern to solve certain specific problems in number theory and abelian groups. Okay, among those problems are quickly finding the prime factors of huge positive integers. Okay, so you could factor an n-digit number using a number of steps that scales only like n squared, roughly, okay, compared to the best-known classical algorithms that have exponential scaling with n, actually with the cube root of n, but same difference for us. Okay, you could also calculate discrete logarithms, including in elliptic curves. Okay, now what is that good for? Well, it just so happens that we, by 1994, we had already made the decision to base the security of pretty much the whole internet on the belief that these specific problems were hard. Okay, so RSA, Diffie-Hellman, elliptic curve cryptography, they're all based on the presumed hardness of these particular problems. Shor showed that if someone builds a scalable quantum computer, then that is no longer true. Okay, and now, 32 years later, we are finally, sort of, I would say, on the verge of actually building scalable quantum computers that are at some point going to threaten cryptography. Okay, but this is all based on the theoretical foundation that we knew already in 1994. Okay, and then so this is a huge application. This shows that a quantum computer can give huge speedups even for problems having nothing to do with quantum mechanics, and it made many other people interested, like the NSA, for example. Okay, this is not. I would struggle to present this as a positive application for the world. Okay, it's good for whatever intelligence agency or criminal syndicate gets it first, especially if no one else knows that they have it. Okay, eventually, hopefully we will all upgrade to use quantum-resistant cryptography, such as that based on lattice problems, and then we'll all just be back where we started, like a giant version of the Y2K problem. Okay, okay, and so then I would say for 30 years, we have been trying to expand the list of applications of a quantum computer beyond just code breaking and quantum simulation, and we've had some modest successes. So there's another very famous quantum algorithm called Grover's algorithm. Okay, and this one has an enormously wider range of applications than Shor's algorithm. This one can give a speed up for just about any combinatorial search or optimization problem that you can name, and even many other problems beyond that. Okay, the issue is that the speed up is much more modest than the one from Shor's. It's typically a quadratic or a square root type of speed up, rather than an exponential speed up. Okay, and for that reason, it's going to be much further into the future that this algorithm becomes sort of a win in practice. Once you factor in the enormous overhead that will come from running a quantum computer at all, right? Like, you know, if you compare n versus square root of n, you know, square root of n is very quickly smaller, right? But if you compare n versus 1,000,000 times square root of n, then, you know, eventually the second one is smaller, but it only becomes smaller after n is in the trillions. Okay, so that's the issue there, and we've been trying to find better speedups than the Grover one for optimization, for machine learning, for AI, but it's been hard. Typically, the speedups we find are either modest, or they're speculative, we don't really know yet, or they're very specialized. Okay, now you know, today there are hundreds of quantum computing startups. Some of them have even gone public. Okay, so there's, you know, billions of dollars of investment in quantum computing. A lot of it is based on the hope that quantum computers are going to revolutionize optimization and AI. So this third category, right? How do they deal with the fact that, you know, the main quantum speedups that we know are only in these first two categories? Well, they came up with like a really innovative solution to that problem, and that was to lie about it. Okay, but you know, since you're listening to my talk, you know, I'll tell you what's the truth. Okay, so okay. Now, for me personally, I like to say that the zeroth application, the one that I care about even more than quantum simulation, is just disproving all the people who said a quantum computer was impossible. Okay, I want those people to have to confront the full truth of quantum mechanics. And I'm optimistic that we're going to be able to achieve at least this one. Okay, so, you know, we have the, in computer science, we like to classify problems into these different categories, like P, what you can efficiently solve with a classical computer. NP is the problems where you can efficiently check the answer with a classical computer. And the hardest problems in NP are the famous NP-complete problems. Okay, and the P versus NP question, one of the great unsolved problems, I would say, of all of mathematics, really, is asking, you know, do these two classes collapse? Okay, but in the meantime, you know, quantum computing has come along and added something new to the story. So BQP is bounded error quantum polynomial time, is sort of the quantum generalization of the class P. I drew it with this wavy boundary, since, you know, everything quantum is spooky and weird. But Shor's discovery was that BQP has certain specific problems, like factoring and discrete log, that we don't know to be in P. It has other problems, like quantum simulation, that we don't even know to be in NP. Okay? But we don't think that BQP contains all of NP. Right? That would, just like we think that P doesn't contain all of NP. Okay, so one of the things that we've managed to successfully do over the last 6 or 7 years is demonstrate what's been called quantum supremacy. I didn't coin the term, by the way, but it's basically just the use of a quantum computer to do something, you know, including the small ones that already exist, to do something that is completely useless, but we think hard to simulate using a classical computer. Okay, so we can now do this. So the first demonstration of quantum supremacy was put forward by Google in their lab in Santa Barbara in 2019. That experiment, you know, it turned like they got all this press coverage for doing it, even though, you know, the problem was completely useless. And, you know, I can say that it's useless because I helped to invent the problem. Okay, you know, the problem was just a sample from a certain probability distribution over, in that case, 53-bit strings. Okay, and just a few weeks later, some folks from IBM said, no, we can simulate this experiment on a classical computer in a much, much faster way than Google realized. So this is not really quantum supremacy, okay? But Google said, okay, fine, never mind. We'll just improve our quantum computer hardware and we will beat your simulation. And by now, I would say, in the view of almost all of us, they've indeed done that. Right? Google, as well as Quantinuum in Colorado and several others, now have devices with up to about 100 qubits, okay, that can sample from probability distributions over 100-bit strings that, as far as we know, using the fastest classical algorithms running on the largest supercomputers that exist, it would take something like 10 to the 25 years to simulate these things, okay? So we get some new information from nature that we couldn't have gotten classically. Not very interesting information, but we get that. Now, one catch is that as far as we know, proving that the quantum computer did the correct thing would also take 10 to the 25 years. Okay, so verification is an issue with these. We can go all the way up to the limit where a classical computer can verify, and up to that limit it works, and then we can continue going beyond that limit. Okay, but what people are struggling to do right now is to just get calculations of a specific number that beat what a classical computer can do, and where you can at least check the answer by comparing to a second quantum computer. Right? And I would say just within the last year, they have started to do that. Okay, good. That's what I said, right? So for example, with simulations of this, what's called the Fermi-Hubbard model and these out-of-time order correlators, we actually have some verifiable quantum advantages that at least as of today, no one knows how to simulate with a classical computer in any reasonable amount of time. So on that basis, I think that this is real. I think that within the next couple of years, we're going to start seeing scientifically interesting simulations that can only be done using a quantum computer, that will tell material scientists, for example, relevant things that they didn't know before. And after that, we can worry about, can we do something useful to for the battery industry or the photovoltaics industry or whatever. And then breaking the public key cryptography, that comes later. Okay, so now, I want to tell you what was the original reason why anyone cared about this, right? It was not breaking cryptography, right? It was not solving problems faster. David Deutsch, the co-founder of the field, was really just thinking very hard about what's called the many worlds interpretation of quantum mechanics. Okay, the many worlds interpretation of this guy, Hugh Everett, is the view that says, the way to understand the world in light of quantum mechanics is simply to say that the giant list of amplitudes is reality. Okay, it is the deepest, ontological layer of the world that science has been able to tell us about, and there is just sort of a quantum state for the whole universe. Okay, and that just evolves in time by the Schrödinger equation, which is the main equation in quantum mechanics, and this whole business about when you look, you see only one outcome. All of that is just kind of an illusion. Okay, that's just an artifact of us being part of the quantum state of the universe. Okay, so what Everett would say, for example, is that if you measure a qubit, that is in a superposition of the 0 state and the 1 state, so it's in a state like alpha 0 plus beta 1. And then this usual quantum mechanics textbooks would say you are going to see the outcome 0 with probability alpha squared and 1 with probability beta squared, right? But then, the whole problem with quantum mechanics for a century has been, well, what do we mean when you look? The laws of physics are not supposed to have a special rule for what happens when you're looking, right? And Everett would say, indeed, there is no such rule. Indeed, all that happens is that you now become entangled with the qubit. Okay, so the quantum state of the universe evolves to something like alpha amplitude alpha, the qubit is 0, and you have registered it being 0. Your measuring device, your brain, the atoms in the room have all registered that it's 0. And then with amplitude beta, the qubit is 1, and you've registered that it's 1. And now these two branches just continue to evolve. They're not going to interact with each other again until the heat death of the universe. So this would lead to a view where reality just keeps splitting into these different versions. This would not just be in quantum mechanics experiments. This would be happening constantly. Okay, and we just experience one of the branches, but all the other branches would be equally real. When I teach my undergraduate quantum information course, I say, look, consistent with the policies of the state of Texas, and especially nowadays, right? I'm not going to impose religion on you. I don't want to get fired for favoring any one interpretation. I will just teach the controversy. Right? You can believe in many worlds if you want, okay? Or, the main alternatives, you can believe that, yes, there is this giant vector of amplitudes, but, only one of the branches is actually lit up by the light of consciousness and experience and so forth, right? The one that we're in. All the others are there in the equations, but they're just kind of ghost towns. No one is actually home to experience anything. That's kind of what Bohmian mechanics says. Okay? Or you could believe that quantum mechanics is not exactly true, right? So maybe, when superpositions get too large, then there's some new law of physics that causes them to collapse to a single outcome. Maybe that new law will even prevent us from building scalable quantum computers. I don't expect that. Okay, I think, if that were true, we would have seen it by now. Okay, but, that's a view that it makes a falsifiable prediction, and, it might be true at some scale that we haven't tested yet, right? Or, there's the original view of Niels Bohr and Heisenberg and the other founders of quantum mechanics, which is basically just a very fancy way of saying, shut up and stop asking these questions. Okay, these questions are outside the scope of science. Physics doesn't have to answer such things. Okay, now David Deutsch, who is, as I said, co-founder of quantum computing, is a very, very hardcore many-worlder. He says that the many-worlds interpretation just is quantum mechanics. Okay, there's that, and then there's just people deluding themselves. Okay, and he has given quantum computing as an additional argument for many worlds. Actually, he says that many worlds is proven even by the two-slit experiment. Okay, so like from the very beginning, he thinks it was the only sane interpretation. But like for those who were too dense to see that, he says, a quantum computer ought to help them. Right, and here's his famous quote from 1997. He says, to those who still cling to a single universe worldview, I issue this challenge. Explain how Shor's algorithm works. I don't merely mean predict that it will work, which is merely a matter of solving a few uncontroversial equations. Deutsch was never a detail guy. Okay? I mean provide an explanation. When Shor's algorithm has factored a number using 10 to the 500 times the resources that can be seen to be present, where was the number factored? Okay, who factored it? How was the computation performed? Okay, so this is his challenge. Now, what do I say about this challenge? So first of all, we should clarify that almost every expert, regardless of whether they're for or against many worlds or they think the question is meaningless, they agree that Shor's algorithm will work, right? Deutsch himself thinks the two-slit experiment already proves many worlds. Okay, but the philosophical question, we could say, is there any sense in which scalable quantum computing, either the idea today or hopefully the demonstrated reality soon in the future, adds to the case for many worlds? So my view is that, yes, at the core of Everett's picture is the exponentiality of this vector of amplitudes. And yes, quantum computing is unique in how it makes that aspect of quantum mechanics impossible to wave away. But on the metaphysical question, like, is anybody home in the other branches? Like the point where many worlds differs from Bohmian mechanics, for example, quantum computing is completely silent about that, right? And there's even a further point, which is that ironically, to whatever extent you can get all these branches to interfere usefully in a quantum computation, well, to that extent, you could say that they never really sprouted off into separate universes at all. Right? Because they, you controlled them so well that they were all part of this one interfering quantum mechanical blob. Right? So this gets into like what is even the definition of a different universe. Right? It's not really a different universe until it's something that we can't interact with anymore. Right? But once we can't interact with it, well then we also don't have direct evidence for it. So that's kind of the tension here. Okay, so I'm just going, the other things I wanted to talk about are much shorter. Okay, so let me say a little bit about, should there be an inductive bias against physical theories that predict computational superpowers? How could changes to the laws of physics yield superpowers? What am I talking about? I'm talking about here things that would go even far beyond what a mere quantum computer would be able to do for us. So here's one of my favorite examples. Okay, so you've probably heard of Goldbach's conjecture, which says that every even number, 4 or larger, can be written as a sum of 2 prime numbers. As 4 is 2 plus 2, 6 is 3 plus 3, 8 is 5 plus 3, and so forth. Okay, it's been checked up to quadrillions, but there's no proof of it. Okay, but here is how we could build a physical computer that will answer the question in merely 2 seconds. We merely have to build our computer so that it checks the first case in 1 second, then the second case in half a second, then the third case in a quarter second, then the fourth case in an eighth of a second, and so on, so that after 2 seconds, it will have tried all infinity cases. Okay? So, you could ask, why doesn't anyone try that? And to some extent, people do. There are people who try to overclock their microprocessor. Okay? But if you run your microprocessor too fast beyond the recommended speed, the problem is that it will melt. Okay, and this is why computers have fans, right? This is why a lot of the cost of running a data center is the cooling, right? But you could ask, what is the fundamental limit here, right? As you run your computer faster and faster, you need more and more energy to run it, okay? And as far as we know, the fundamental limit here would come when you would run at about 1 step per Planck time, which is 10 to the 43 operations per second. Okay? At this point, if you had a computer that would run that fast, it would exceed its own Schwarzschild radius. Okay? Which is a fancy way of saying that at that point your computer collapses to a black hole. Okay? I've always liked that as nature's way of telling you not to try something. Okay? But seems like we really do need to bring in our knowledge about physics to rule this out. Okay, which is interesting. Okay, another example is what I call the relativity computer. Okay, this is where you start your computer working on some very hard problem. You leave your computer on Earth, then you get in a spaceship. You accelerate to nearly the speed of light. You decelerate. You return to Earth. In Earth's reference frame, billions of years have passed, all your friends are long dead, civilization has collapsed. But if you can still find the computer in the rubble, somehow it was still running, then you can read out the answer to your hard problem. So again, why doesn't anyone try it? Well, again, I think the fundamental limitation here has to do with energy. It has to do with how much energy would it take to accelerate to that close to the speed of light that you would actually see such a speed up. Okay, there are other ideas, quantum computing using time travel into the past closed time-like curves. This is a really fun one, but I'll probably skip it for lack of time. Get it? You know, if people want to ask me about it afterward, I'll be happy to tell you about it. Okay? But you know, so the question I want to ask is, should, you know, if someone comes along with an idea like this, that, you know, you could solve, you know, these impossible problems by just arbitrarily speeding up time or going back in time or something like that, should you say that this idea is disfavored because if it was true, then it would posit too much computational power on the part of nature? Like, is that an argument? Now, my own view is that we can't be too dogmatic about this, because if we were, we would rule out quantum computing and arguably quantum mechanics itself. Okay, not only that, but some of my friends in computer science who still don't believe in quantum computing, even after all the experiments that we've done on quantum supremacy, like that's basically their view. You know, if you look at Gil Kalai or Leonid Levin or Oded Goldreich, people like that who don't believe in quantum computing, they seem to just take it as an axiom that, you know, nature can only do the problems in P, you know, can do classical computation. Why is quantum computing impossible? Because it violates that axiom, right? So, you know, I don't want to be that dogmatic. You know, I do believe that quantum computing is possible, okay? But, you know, saying that there is no fast way to solve NP-complete problems in the physical universe, to me it feels kind of similar to just saying, you know, there is no faster than light communication, or there is no perpetual motion machine. That is, these are all empirical statements, right? They're not statements of logic, right? They could be falsified tomorrow by an experiment, okay? But if they're falsified, then so much of what we believe about physics would fall with them, okay? And not only that, but it turns out that the same physics hypotheses, like closed time-like curves or modifications of quantum mechanics to make it nonlinear, they tend to violate all three of these principles at the same time. Of, you know, they let you solve NP-complete problems, they let you send messages faster than light, they let you violate thermodynamics. So it seems like there's some connection here, and that, you know, maybe we should just take any theory that violates that as having an extra burden of proof that it would need to meet. Okay, so, and then the last thing was the idea of complexity as armor. Okay, so can we delimit the range of validity of effective theories in physics by saying that it would take astronomical computation time to engineer the breakdown of our effective theories? So this seems like a funny idea, but it sort of came to broad attention, as I said, 12 or 13 years ago, via these new insights that people had into the black hole information paradox. Okay, so the information paradox is this question that Stephen Hawking asked half a century ago. Okay, he asked, what happens to information that falls into a black hole? Okay, and according to general relativity, it should just fall into the singularity and then just sort of disappear from our space-time manifold. It should never be accessible again. Okay, but quantum mechanics, certainly in the many worlds version, says that everything should be reversible in principle. Right? No information should ever be truly destroyed. Okay, so you had two basic principles in conflict with each other, right? Which is historically the way that physics has made progress, by trying to resolve these conflicts. Okay, and of course Hawking also discovered that black holes very, very slowly radiate and disappear into a mist of Hawking radiation. And so then the idea was, could the information somehow come out in the Hawking radiation, even though existing physics doesn't seem to allow that? Okay, So people had a bunch of ideas about this over the decades, about how like there are multiple points of view. There's the point of view of the outside person and the point of view of someone who jumps into a black hole, which look very different from each other, but it's all okay as long as those two people can never meet each other to compare notes. Okay? That's basically the idea of complementarity, which was of Lenny Susskind that Girard had hoofed. Okay, but then that turned out to not really work. There was another thing called the firewall paradox, and there was this experiment that people realized that you could do where if you monitored Hawking radiation coming out of a black hole and then you jumped into the black hole, then at the when you hit the event horizon, you would just see basically an end of space-time, right? You would not be able to cross the event horizon. Okay, and like physics is supposed to break at a black hole, known physics, but only when you hit the singularity, right? If it's already happening at the event horizon, then something is happening that's not supposed to. Okay, and so the clear prediction was that Alice would just burn up at the black hole interior, and this violated general relativity and quantum field theory, even in the low energy regime where they were supposed to be valid. Okay, so the amazing idea of Harlow and Hayden, which I then helped to refine, was that yes, in principle this is true, but this only happens because Alice can see non-random patterns in the Hawking radiation before she jumps into the black hole. And to see those patterns, Alice would need to solve a computational problem. Okay, that, yes, in principle, it is solvable. She has enough information once the black hole has more than halfway evaporated. But to actually do it, she would need to solve a problem that would take exponential time, even for a quantum computer. Okay, or seems to. So now, a black hole should evaporate in about 10 to the 67 years. Okay, so for all these experiments, we assume you have a very long grant. Okay, but for this, we were saying to actually do this quantum computation, Alice would need to spend 2 to the 10 to the 67 time. So before she could, made a dent, the black hole would have evaporated. So there's no problem. Nature is sort of preserving its, the appearance of general relativity and quantum field theory via computational hardness. That was the new part here. Okay. And you could say, would a contradiction in physics be okay if it took exponential time to uncover it? That would be a really, really weird thing to say. Now, to be fair, I don't think that's what Harlow and Hayden are saying, right? What they're saying, the contradiction is only in our effective field theories, GR and QFT, right? Whose regime of validity is now protected by a computational barrier alongside the usual energy barrier. The true theory of quantum gravity that we don't know yet, that would presumably be free from contradiction. Okay? So in very recent work with Gulchakardis and Harrison-Hartle, we applied a similar idea to the second law of thermodynamics itself. So what we did is we constructed a toy situation where if P were equal to NP, so if you had this computational superpower, then you could appear to reverse the second law of thermodynamics by building a Maxwell's demon that would sort of take the gas in a box and sort of collect all of it onto one side of the box. Now, this demon would not really be decreasing the total entropy of the universe, which is impossible, but what it would be doing is decreasing the pseudo-entropy. Okay, so there are situations where you could have a lot of what looks like entropy, but is actually compressible if you solve a hard enough computational problem. Okay, and that's what happens in our toy scenario. Basically what happens is that the demon collects all the gas onto one side of the box, and in the normal story about Maxwell's demon, this does not contradict thermodynamics because the demon, the entropy has to go somewhere. And where does it go? It goes into the demon's own memory, right? Into its own brain, okay? But now what we're adding is that in these situations, if P were equal to NP, then the demon would be able to compress its memory, right? It would be able to take all this seemingly random data in its memory and compress it down, and thereby really appear to reverse the second law. So there are some situations where the second law appears to be true, but only because P is not equal to NP, or because pseudo-random generators and one-way functions, things like that exist. Okay, and we did a little simulation of our scenario. Okay, so concluding thoughts. More than a century ago, knowledge and information, despite their apparent human-centricness, snuck into our best explanations in physics via Boltzmann and statistical thermodynamics, via the no signaling principle in relativity. So should we be so surprised if computational limits likewise sneak into physics explanations in our own time? Now, one difference is that progress in pure math, like a solution to the P versus NP problem, which would be nice, could help clarify which of the computational limits are real. And if you want to learn more, back in 2011, I wrote a survey article called Why Philosophers Should Care About Computational Complexity that covers most of what I talked about today, although not the most recent stuff. So with that, it's been 1 hour. I hope that was the right time. So thanks for listening. Happy to take questions.
¿Preguntas?
Hi, thank you for the explanations. Do you think something about computing or algorithms belongs more to the natural world rather than the mathematical world?
That's a good question. I think it's really in between, right? Like I love being in quantum computing simply because I'm not forced to choose. Do I want to talk to physicists, computer scientists, mathematicians, even philosophers, right? These boundaries are all just sort of very permeable, right? And I can talk to all of them. I mean, I think, what I hope that I've illustrated in this talk is that I think a computational lens is extremely useful in the natural sciences, certainly in physics, where, it's had a huge impact on how we think about quantum mechanics. Right, and even quantum gravity these days. But I think the computational lens has also been very, very useful in biology, thinking about protein folding, about evolutionary dynamics, in economics, in sociology, thinking about algorithmic game theory, things like that. So I think it really is a useful lens. Of course, you can also think of at least the theoretical part of computer science as a branch of mathematics. That's also a valid way of thinking about it.
Okay, thanks. But do you think that usefulness comes from the fact that we are actually studying something about the natural world, or just like good casualty that our model works very fine?
Yeah, well, I mean, I think the notion of computation is so broad that, you can regard just about anything as a computation, right? Anything that is following any kind of rules, right? So that could be, a brain, it could be birds flocking, it could be a bacterium, it could be, all the quarks and gluons inside of a proton, or it could be a digital computer with transistors. That's just another example of a computational process. Right, the question is, when is this lens a useful one? Right? If you just say, oh yeah, dude, the whole universe is a computer, right? You can say that, but you have to go further than that for it to become useful. Right? You ask, well, what kind of computer is it? How many bits does it store? How many operations can it do? What kind of operations? And then you can actually start to get very interesting answers.
Thank you very much.
Yeah, sure.
¿Otra pregunta?
Thanks for coming. Very brilliant.
Thanks for having me.
And funny. I saw your Lex Friedman interview. Very, very nice.
Thanks.
Some conference.
Thanks.
What do you think that we can learn in the case of research in in a quantum Riemann hypothesis?
Quantum Riemann hypothesis? So I am really far from an expert on the Riemann hypothesis. I mean, I know what it says, right?
Yes.
But the one little thing that I do know here is that there is a famous approach to the Riemann hypothesis that originates with Freeman Dyson in the 1970s that basically says if you could find some Hamiltonian operator, right? Which would have to be a Hermitian operator, right? Was such that the zeros of the Riemann zeta function would be the eigenvalues of that operator. Then that would give you a proof of the Riemann hypothesis, right? Because the Hermitian operator has only real eigenvalues, and that would show you that all the zeros would lie along one line, right? So people have tried that approach since the 1970s. They've tried to construct a quantum system such that the zeta zeros are the eigenvalues of that quantum operator. They've not succeeded yet. It's not something that I've ever worked on, nor does my expertise on it extend beyond basically what I just told you.
Okay, very nice. Second, Juan Maldacena, that has been working in the holographic principle. He said in a conference that maybe with 10,000 qubits, you can simulate a universe. So I would like to know.
I mean, I think, ironically, learning new things about models of quantum gravity might be one of the early applications of a quantum computer, right? It sounds like something very exotic, okay? But the difference is if you want to simulate, let's say, chemical reactions, right, there's all kinds of fiddly details that you have to get right. Right, because you have to encode electron orbitals into qubits, and this costs a lot of qubits, a lot of operations, right? You have to compare to experimental reality, right? But quantum gravity, is a field where people just kind of make up models, right? That kind of, they say, what if the universe were a lattice of qubits? And we say, oh, a lattice of qubits, that's what we have in our device. Right, that maps very neatly onto the kind of hardware that we're building, right? And so we can start testing these models of quantum gravity possibly in the near future. I agree with Juan about that. Now, unfortunately, like anything, people will hype this beyond, right? That there was a claim a few years ago that Google had created a wormhole using its quantum computer in the lab, okay? What they actually did is that they used like a tiny 9-qubit quantum computer to do a little toy computation that could be interpreted as a simulation of a holographic theory that has a dual description involving a wormhole. Okay, you learn nothing that way that you couldn't have trivially learned by just simulating it on a classical computer, right? And then it turned out that they didn't even do it right. Okay, so that was the wormhole in a lab thing. Okay, but I think that eventually, yes, we will have more serious versions of that with hundreds of qubits, and hopefully we'll learn things about whether we're learning about nature itself. I don't know, but at least the predictions of these models of quantum gravity, right? We'll be able to learn things that we were not able to calculate with classical computers. Yeah, I think Juan is right about that. Hey.
Amazing presentations. It's
Thanks.
Amazing.
Thank you.
And really funny.
Thanks.
Also.
Thanks.
I have 2 questions.
Okay.
You have argued that complexity theory is the deepest lens we have on computations, but with AI empirically outrunning theory, systems that work without us understanding very well why. Do you think the next foundational breakthrough will come from within complexity theory or from somewhere theory hasn't looked at yet?
Yeah, so first of all, nothing I said in this talk rules out the possibility that soon, everything that we do as humans, AI will do better, right? And then where does that leave us, right? That's a very big problem, one that is sort of looming over everything else that we could possibly think about or do. I am trying to do what I can there. I took a 2-year leave recently to work at OpenAI. I joined them back when they were saying, we're just a little nonprofit trying to do this right in the interests of humanity. We would sooner dissolve ourselves than race to build an AI that was not safe. They're not really saying that anymore. Okay, but I was at OpenAI to witness that change happen, let's say, and now at UT Austin, in addition to the quantum information group there, I also run a group on theoretical computer science and AI alignment. So we're trying to figure out, can anything in complexity theory be used to help AI go better, right? But, of course, the other direction here is that we can use AI to help with, theoretical computer science research, with quantum computing research, as just a special case of the fact that we can use it to help with anything, right? So, I mean, within the last 6 months, like when I have a calculation, that I need, or a lemma, that I need to prove for a paper I'm writing, like the first thing I do is I ask GPT 5.2 Pro. And sometimes it proves it for me, And I'm sure that this, is making my own skills atrophy, even more than they already were just from my getting older. Okay, but so I'm not sure if I like the world that it's leading to. Okay, but 2 or 3 years ago, maybe it was a joke. It's not a joke anymore, right? People are actually publishing math papers and physics papers where they used GPT to help them do the research. And this is the worst it's ever going to be, right? It's just getting better and better from here. So of course that's going to affect everything we do. Now, one thing that I don't think that you can point to yet, I don't think there is any profound insight, on the order of general relativity or Gödel's incompleteness theorem that you can say an AI thought of that. Okay, but maybe that's just a matter of years. I don't know.
Thank you.
Yeah.
I think we had one more question.
Well, first of all, as others have said, a surprisingly and refreshingly funny talk, so thank you very much.
Too kind.
Hope other people can learn from your example. I just wanted to ask, and I hope you're right, because proving people wrong is one of the most amazing feelings there are. Aside from what I can guess are incredibly complex and difficult engineering problems, are there any theoretical snaggles or divides that you think will be tipping points in quantum computing? And are there any that you find personally fascinating that you could share with us?
Yes, okay, so quantum computing theory remains, a very, very vibrant area, right? We are trying to we're still trying to figure out what exactly is a quantum computer good for. What is it not good for? Okay, we're trying to figure out, how does quantum mechanics change the whole theory of computation? Like, you could take any concept from classical computer science, communication or interactive protocols or, a one-time pad or this or zero knowledge, and you can put the letter Q in front of it, and you can see what happens, and that's been keeping us busy for decades now, okay? There's also lots of theory work that's going into, the design of better quantum error correcting codes, right? So you could say that, in building a scalable quantum computer, there's sort of two sides to the engineering problem, where the first side is getting better and better hardware, that can control the qubits better, building that hardware at scale, okay? But then all hardware will be subject to some error, right? And so then the second part of the problem is designing schemes for error correction, okay, that can cope with larger amounts of error or that are more efficient to use or that have lower overhead. Okay, and so people have been, as the experimentalists have been making progress on the hardware, the theorists have also been making a lot of progress on coming up with better ways to do error correction. And the reason why we're at such an exciting moment right now within the last couple of years is that the two sides seem to have kind of met each other at this point, where we have 99.9% accurate 2-qubit gates, and we have error correcting codes that can deal with 0.1% error, right? And so I feel like if there were some fundamental showstopper, then why hasn't it shown up by now, right? Like, it seems like at this point, it should really just be a matter of scaling up what we have. But of course, until you actually demonstrate the machine that can factor the 10,000 digit number, I don't think, these skeptics are going to change their minds, right? Hopefully, once you have that, then they'll change their minds. They won't say that, it must be the devil interfering with my senses or something like that.
Thank you.
Yeah.
Maybe we have time for one more question.
Hi, Scott. So you were talking about the usefulness of quantum computing to simulate quantum physics itself, and how about simulating the brain? I mean, is there anything known about whether to simulate the brain you would need quantum computing?
Yeah, okay. It's an interesting question. People have thought about it, but I think the answer depends enormously on at what scale are we trying to do the simulation. If we're trying to do a simulation like at the neural level, right? So we're modeling each neuron as sort of a type of logic gate, that either fires or doesn't fire, depending on, the incoming signals, maybe has some little bit of internal state to it, right? Then at that point, this seems very much like classical computation, right? This seems like I wouldn't know how to get much of an advantage, even once you have a fully, fault-tolerant quantum computer, except possibly the Grover advantage here and there, right? But not like a game-changing kind of advantage, right? And this is also what I would say about using quantum computers to speed up kind of existing deep learning, or existing neural nets, right? Like maybe there's some Grover advantages here and there that are eventually relevant, but it doesn't seem like a game changer. Now, what would be a game changer would be if you needed to simulate like the individual neurotransmitters, right? If you needed to go in, to like simulate at the biochemical level inside the neuron, then that's where you're actually going to see quantum effects that are not just washed out, by scale. And maybe, if someone believed that quantum effects were important there, then maybe a quantum computer helps there, right? Of course, Roger Penrose famously believes not only do quantum effects matter, but that there has to be some new theory that would go even beyond quantum mechanics, and that's implicated in his theory of consciousness. Okay, he believes a lot of things that that most of the field does not believe. Okay, if you had a more standard view that the neurons are kind of like transistors, they fire or they don't fire, you just need to simulate at the level of the neurons and synapses, then to me that seems mostly like classical computation.
Había una pregunta más donde.
Oh, there's back there.
Hi, thank you for the talk. I just wanted to ask, what's your opinion on hypercomputation?
Yeah, well, so I talked about that in the talk, like that finite time Goldbach decider that checks an infinity of cases in 2 seconds, right? That was a hypercomputer. Okay, I didn't use the word, but that's the word that people use in the philosophy literature. So basically, I think that this entire literature on hypercomputing has sort of the fatal problem that it ignores, everything we know. It ignores sort of, let's say, the entirety of what we know about physics. Often they're just looking at classical general relativity or like Newtonian physics, and they're just ignoring that our world is quantum mechanical. Right? And once you bring in quantum mechanics, well, then you have to deal with the Planck scale. It's not optional, right? And I think once you do that, the argument I was making was that basically kills the hypercomputing proposals that I know about.
Okay, so would you say the universe is a hypercomputer, or?
Well, I mean, based on the quantum mechanics and the other physical theories that we know, it seems like, so I didn't really talk about this in the talk, but there's this Bekenstein-Hawking limit, right, that seems to like upper bound the number of bits that you would need to describe any bounded region of space by basically about 10 to the 69 bits per square meter of surface area. Or, in the quantum case, 10 to the 69 qubits per square meter. That's an enormous number, but it's a finite number. Okay? We don't know how that ultimately gets implemented. That's a problem for quantum gravity to solve. Okay? What we know, incredibly, is mostly just the number. We know how much entropy there should be there. Right? If that is true, then that would seem to say that no, our universe is not a hypercomputer. Our universe is merely a quantum computer. It is merely a collection of, some finite collection of qubits that are evolving in time by the equations of quantum mechanics and so forth. For it to be a hypercomputer, something would need to be wrong in that picture of quantum gravity.
Thank you.
Sure.
Sé que hay más preguntas, pero creo que ya fue bastante tiempo.
Right.
Vamos
I'm happy to
Scott se vaya.
stick around a little if people want to.
Well,
Yeah.
we can go outside. There's
Oh, okay, yeah, sure. Okay, perfect,
Can
perfect,
approach you.
perfect,
Yeah.
perfect.
Entonces, démosle las gracias a Scott de nuevo.
Okay, good.